This is week 8 Introduction to Coding 3 problem solving session by Sachin, myself, PhD scholar in the Indian Institute of Science. Now, this week we will be solving questions based on turbo codes and automatic repeat request schemes, and some questions on applications of linear codes. First question: what is the IRWEF of a 6.5 parity check code SPC is given by six five SPC has five information bits and one parity bit, and the parity bit is equal to the mod 2 sum of all the information bits. So with 5 bits, there are 2 power 5 is equal to 32 input combinations. So 32 input, uh, yeah, 32 different input messages are possible, and one code word is assigned for each by appending a parity check bit at the end that is equal to the uh, mod 2 sum of all the information bits, so that when you do the mod 2 sum of the entire code word, it will always be 0. For such a code, the code words will be of the following one. Uh, that's the if that is the information that you have, or the if that is the input message, then since the sum of the bits is 0, or the parity bit is 0, or 0 is appended, so you get a 6-bit code word from a 5-bit information sequence. And there are 32 such possibilities. So for 00000, parity bit is 0. For 00001, parity bit is 1, and so on up to finally you get 11111, and the parity bit will be 1. So the parity bit is such that there are even number of ones in the code word. That's all. Now to calculate the IRWDF, WEF, the weight and enumerating function, you can write that as A of W comma uh, Z would be the sum of Aij W power I Z power J for all code words. I the weight we could write Aij is the number of code words with input weight, and by weight we mean the Hamming weight, input weight I and parity weight J. So if the parity bit is 1, you have a Z, And if the parity bit is 0, you have Z plus 0 is 1. So for the above SPC, there are one code word of weight 0 and parity with input weight one code word of input weight 0 and parity weight 0. There are five code words of input weight 1 and parity weight 1. There are 10 code words of input weight 2 and parity weight 0. 10 code words of input weight 3, parity weight 1. 5 code words of input weight 4, parity weight 0. And 1 code word of input weight 5 with parity weight 1. So that means the A of W comma Z is 1 plus 5WZ plus 10W square plus 10W cube Z plus 5W power 4 plus W power 5Z. And that is the IRWA function. Question 2 asks the following. Consider PCBC parallel concatenated block code with 6-5 parity check code as constituent encoder and interleaver size capital N is equal to K. The average CWEF for input weight to is so the average it's a parallel concatenated block code with interleaver size N equals K. So we have seen in lecture that the average CWEF of the PCBC were two systematic MK constituent codes C1 and C2 with CWEF given by AW C1 of Z. So if constituent codes C1 and C2 have average CWEF conditional weight enumerating function as AWC1 of Z, uh, usually use small w here, and AWC2 or Z. Then by concatenating these to get a parallel concatenated block code, you will get a code with average CWF equal to AW of the parallel concatenation of Z is the product of the average CWF of the two codes divided by n choose W, where n is the interleaver size and W is the weight of the input for which we are calculating the weight enumerating function. So here for this question, for input weight 2, that means W is 2 and n is equal to k. Since we are using a 6-5 parity check code from the previous question, the 6-5 parity check code, which is an NK code. So K is 5 information bits, and code word length n is 6. So K is 5. That means interleaver size is also 5 here. So n choose W is 5 choose 2, 10, and C1 and C2 are both the same SPC we saw in the question 1. So AW C1 of Z here, of course, W is 2 into A2 C2 of Z is, so the conditional weight enumerating function is nothing but the coefficient of the W term corresponding to the given weight. So when weight is 2, the W term which has power 2, which is W square, the coefficient of that is the conditional weight enumerating function, average conditional weight enumerating, the average CW here. So AW A2 C1 of Z and A2 C2 of Z are both 10. So this will be different in different codes. It's 10 only in this. This term might have had Z or a combination of powers of Z. So you will have to write that also. Here we don't have Z here. That's why he had here it's a function of Z, but for our question it's a constant function of Z and its value is 10. 10 times 10. Since we are using the same SPC for both C1 and C2, both of them have the same average CWF for weight 2. Now substituting these things into the formula, which will give you A2 of the parallel concatenation, Z is 10 times 10 divided by 10, which is 10. Question 3. So consider PCBC with 6-5 parity check code, 6-5 SPC as constituting constituent encoder and interleaver size n equals k. The average IRWEF is given by now the average IRWEF function is given as AW PC of W comma Z is the summation of AW PC of Z multiplied by W power W. So here it's in the first question what we saw was the IRWF of only one of those codes, one of the constituent encoders, A of W comma Z. But here you have a parallel concatenation of two such encoders. So you're taking the average, and you take the average. Here also you saw uh, you have powers of W, and the powers of W are the weights of the input sequence multiplied by the number of code words having that input weight and multiplied by the power of Z, where the power of Z is the weight of the parity bit. So again, the average IRWF will have powers of W multiplied by number of code words. Uh, or number of Okay, so the coefficient of a power of W is the average CWF. So here it's just the CWF since you have only one code in the first question. So for W is equal to 2, the CWF would just be 10. W is equal to 3, the CWF would be 10 power Z, and so on. But in a parallel concatenation, you will have to replace that by the average value. So the formula will turn out to be again, you will have some power of W, where the power of W is the weight of the input sequence. Weight of the input sequence can vary from 1 to capital N here, since N is equal to K. There are K input symbols. If all of the K input symbols can be 1, input bits can be 1, which will give you input sequence of weight K. All of them can be 0, which will give you an input weight of 0, or they can be something in between those two. So we have the sum of weights of W multiplied by the average CWF. Average CWF, we saw the formula for that in the previous question. We'll have to do that for each of the weights, W varying from 1 to K. So here K is 5, so from 1 to 5, you'll have all the terms. We I taught you how to do that in the previous question, so you can carry out the operations yourself. You'll get A1 of PC comma Z is 5Z square by Phi C1 is 5z square. So 5z for W1. And we saw A2 PC of Z in the previous question. It was 10 from question 2. A3 PC of Z will be 10z square divided by 5C3, which is equal to 10. So 10z square by 10 is 10z square. A4 PC of Z five square divided by 5C4, which is nothing but 5, so it's 5. Finally, A5 PC of Z is simply Z square divided by 5C5, which is 1. So it's only Z square. Okay, now we plug those values into this formula. We'll get AWPC of Z AWPC of W comma Z is equal to 5WZ square plus 10W square plus 10W cube Z square plus 5W power 4 plus W power 5 Z square. Okay, I'll take a short break and come back and continue from question 4. All right, let's continue with question 4. Which of the following statement statements regarding convergence of turbo codes is false? First option is existence of tunnel in exit chart implies convergence of turbo decoding. That's a true statement. El-Gamal's approach for predicting decoding threshold for turbo codes is based on Gaussian approximation of the output extrinsic information. That's a true statement. Convergence analysis of turbo codes assumes large input block sizes. It's also a true statement. So finally, none of the above. Actually, well, I said this in the last class also, but they are asking which of the statements is false. So the first three statements are not false. That means the statement, none of the above statement is false, is a true statement. So actually, all four of them are true statements. It will work if they're asking which of the following is a true statement. Say none of the statements are true statements. Then none of the above is a true statement. Would itself be a true statement, so that would be what you mark. It doesn't work when you're asking which of the following statements is false, because the option none of the above statements is false. None of the above means none of the above is false. Is actually a true statement. So it's a semantic game I'm playing, but you know what they mean by that. You should know by now. So the option none of the above is correct. Technically, it's not, but for our purposes, we'll assume you know what we mean. Question 5, the generator polynomial. Now we have moved on to ARQ, automatic repeat requests. The generator polynomial for a 11.7 code. By 11.7 code here, you know the context. It's from week 8, so it's a CRC code. 11.7 CRC code is g of x equals x power 4 plus x plus 1. For the input sequence 1110001, the parity bits C3, C2, C1, C0 are given as. Here's the solution. By the way we construct, the way we write the parity bits is such that if there are 7 information bits, you can write that as A6, A5, A4, A3, A2, A1, A0 is the information sequence. Then the parity bits C3, C2, C1, C0 are such that g of x divides c of x, where c of x is the polynomial a6 x power 10 plus a5 x power 9 plus etc. a0 x power 4 plus 3 c3x cube plus c2x square plus c1x plus c0. So we have to get a remainder 0 when we divide g of x by uh, when we divide c of x by g of x. Here g of x is x power 4 plus x plus 1, and substituting the value of a6 to a0 in the above equation, the information sequence is 1110001. So you get x power 10 plus x power 9 plus x power 8 7, 6, and 5 have coefficient 0. X power 4 plus C3x cube plus C2x square plus C1x plus 10. Ah, sorry, I couldn't understand my own handwriting. It's C0. It's not 10. Okay. Now let's carry out this division. X power 6 multiplied with x power 4 plus x plus 1 will give you x power 10 plus x power 7 plus x power 6. Subtract and you get x power 9 plus x power 8 minus x power 7 minus x power 6 plus etc. Then uh, you multiply by x power 5, get x power 9 plus x power 6 plus x power 5. So when you subtract, you get x power 8 minus x power 7 minus 2 times x power 6 minus x power 5 plus x power 4 plus etc. Then you multiply that by x power 4, you'll get x power 8 plus x power 5 plus x power 4. When you subtract, we'll be left with x power 7 minus 2 times x power 6 minus 2 times x power 5 plus c3x cubed, c2x square, etc. Then you multiply that with x cube, get x power 7 plus x power 4 plus x cube. When you subtract, left with minus 2x power 6 minus 2x power 5 minus x power 4 plus c3 minus 1x cube c2x square plus c1x plus c0 multiplied by minus 2x square will give you minus 2x power 6 minus 2x cube minus 2x square will be left with minus 2x power 5 minus x power 4 plus c3 minus 1 plus 2 c3 plus 1 x cube plus c2 plus 2 x square plus c1x plus c0 minus 2x will give you minus 2x power 5 minus 2x cube minus 2x minus x power 4 plus c3 plus 3x cube plus c2 plus 4 Sorry, I have a call. I'll be back. Hello. Hello. Okay, I'm back. Oh, sorry. Okay, that's what you have. That's the remainder. C3 plus 3x cube plus C2 plus 4x square plus C1 plus 3x plus C0 plus 1. But we are operating in mod 2, so it doesn't really make sense to. C3 is a bit. What do you mean by adding the 3 to a bit? So we are actually operating in a mod 2 domain. So in mod 2, 3 is what? It's just 1. It's 1 plus 1 plus 1, but 1 plus 1 is 0. We are left with 1. So this is equal to C3 plus 1 x cube plus 4 is what in mod 2? It's 0 in mod 2. C2 x square plus. Of course, you could have done the mod 2 operation right from the beginning, but uh, modulus works in such a way that you can do all your operations and change your coefficients numbers to mod 2 anytime you want. in any step. So this is again C1 plus 1x plus C0 plus 1. Now g of x must divide c of x. So c3 plus 1 equals 0. Coefficient of x cube should be 0. So implies c3 is 1. c2 is 0. c1 plus 1 must be 0, which implies c1 is 1. c0 plus 1 is 0, which implies c0 is 1. So c0, c1, c2, c3 is 1, 1, 0, 1. That's all. Quite simple, as long as you know how to do polynomial division. And you don't forget that you are in mod 2 space. Question 6. In the go back N ARQ protocol, this is the ARQ protocol with a sliding window, and if an error is detected in some frame, you retransmit the entire window starting from that frame. Should have seen explanation must have been given in class. The go back N ARQ protocol, the transmitter uses a 15,11 code. I forgot to highlight this answer. That's your answer. Back to this question 6. 15,11 code, window of length 10, and the probability of acceptance of frame at the receiver is 0.03. The efficiency of the protocol is what? So the efficiency for go back MERQ is given by eta k by n p over p plus n into 1 minus p, which is k is 11, n is 15, p is 0.03 divided by 0.03 plus length is 10, 1 minus 0.03 is 0.07, 0.03 by 0.73, 3 by 73. We will do that. 3 over 73 times 11 divided by 15. They say the answer is 2.3 into 10 power minus 3, but this doesn't give 2.3 into 10 power minus 3. Let me go find my calculator. 0.03 plus 10 times 1 minus p. Oh my god. Uh, this is 0.97. 1 minus point, 03 is 0.97, not 0.07. Now it's fine. 0.97 to 10 is 9.7. 9.7 plus 0.03 is 9.73. 0.03 by 9.73 is 3 over 973 into 11 divided by 15, which is 2.26 into 10 power minus. That is the efficiency of the go back n ARQ for the given parameters. How we got that formula is in the lecture. Oh, and you can go check that out. Which of the following statement about ARQ protocols is not correct? First statement, SR ARQ is the most efficient ARQ scheme. That is a true statement. Second statement, SR-ARQ is the most reliable ARQ scheme. No, 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 no. Reliability doesn't depend on the ARQ protocol. SR-ARQ is not more reliable, not inherently more reliable than other ARQs. A stop and wait or go back in. So that is the first statement. What the C type 2 HARQ is more complex than type 1 HARQ scheme. Part D is undetected error probability of CRC codes depends on number of parity bits. That's also a true statement. All right. Next three questions are not theoretical, thankfully. In the SWARQ protocol, so we found the efficiency for O back N ARQ protocol. This will this is a drill problem finding the efficiency for SWARQ, stop and wait ARQ, for a time of idle time is 10 power minus 1 beta frame units, and N and K values are 15 and 11. We're using a 1511 code. And finally, the probability of acceptance of frame at the receiver is 0.03. The efficiency of the protocol is solution. They highlight the solution previously. Eta is it's different for different protocols. So for stop and wait, it's k by n into p over 1 plus beta. This is 11 by 15 into 0.03 by 1 plus 0.1. 0.03 divided by 1.1 into 11 divided by 50, which is 0.02. Question 9 and 10 are on applications of linear block codes, linear of error correcting codes in real life, simple applications. These should have been included in the first lecture to motivate error detecting codes. I guess the course team had a different vision, but usually these will be given as motivating examples at the beginning of the course. Therefore, which of the following is a valid international standard book number? I won't write the entire thing. ISBN 10 number, and I have to give you the options for that: 48104208991, 38104208991, 38104208990. D, none of the above. Solution. So for this, if the ISBN number is if the ISBN 10 number is A1, A2 up to A10, where A10 is the check digit, then A10 must be equal to A1 plus 2A2 plus 3a3, etc. up to 9an mod 11 for option A. A10 must be 4 plus 2 into 8 16 plus 3 into 1 3 plus 4 into 0 plus 5 into 4 plus 6 into 2 7 into 0 plus 8 into 8 plus 9 into 9, which is in mod 11. So I'll simplify it in this way. 4 plus 16 is 5 mod 11, 3 plus 20 is 9 mod 11, 164 is 9, and this is 4. B5 plus 4, 9 plus 3, 12, which is 1, plus 9, 10, plus 1, 11, plus 9, 20, which is 9, plus 4 is 13, make 2 mod 11, but A10 is 1. So invalid. In B, only the first digit is 3 instead of 4. So 3 plus 16 plus etc. plus 81 mod 11 is nothing but 3 is 1 less than 4. So you're adding 1 less than the previous sum. So this is the same sum where 4 is replaced by 3. So it will be 1 less. So it is 1 mod 11. This is A10. So the code word in option B, 3810420891, is valid. Option C has the same message bits as B, but parity bit is 0, so it is invalid. Final question of the final problem solving session. First 12 digits of Bookland barcode are 978310250849. The 13th digit is, and solution for a Bookland barcode, the 13th digit is such that A1 plus 3A2 plus A3 plus 3A4 plus etc. plus 3A12 plus A13 mod 10 is 0. So 9 plus 21 plus 8 plus 9 plus 1 plus 0 plus 2, which is multiplied by 3, this, and this. is 15 plus 0 plus 24 plus 4 plus 27 plus 813. 0 in mod 10. So 9 plus 1 plus 8 plus 9 plus 1 plus 0 plus 2 plus 5 plus 0 plus. This is 9 plus 1, 10. That's 0. That is 0. This is 0. And you're left with 5 plus 4, 9 plus 4, 13, which is 3 plus 7, 10. So A13 mod 10 is 0. So A13 is 0. The parity bit is 0. That's all. That's the final problem of the final problem solving session for this semester. Hope you learned something. Alright, that's it. See you in the next semester.